Welcome to another mini lecture on Module 7 looking at two sample designs. So the two sample designs that we've been looking at so far have the assumptions that the data from the populations are normally distributed. Other assumptions that exist are that data are independent of random samples from the population and the variance of data from both groups is equal. And an important thing to note is that if the data do not meet these assumptions, our conclusions can be incorrect. For some of these assumptions, there are alternative tests that can be done. That's what we're going to be talking about in this mini lecture. However, not all issues can be fixed. So if data aren't randomly sampled or the variance isn't equal, those are sometimes a little bit tougher to deal with. In the case where the data do not follow a normal distribution, we can do what's called a non-parametric test. A non-parametric test do not require the same assumption that parametric tests require, in particular with the normal distribution. Because non-parametric tests are not used to estimate population parameters, therefore we do not need to assume anything about the population distribution that we're sampling from. Right? So if we're trying to estimate the mean, we need that distribution to have a normal distribution. Like similarly with standard deviation. Well, we can estimate standard deviation when there's a normal distribution in the population that we're sampling. And non-parametric tests work by converting the data from the numbers that we have to ranks, and then we're testing for the equality of the distribution of the data. Now for non-parametric tests, I'm interested in you having an understanding of how they operate and work, but I will not be asking you to do detailed calculations for them. So when we're doing ranking, ranking involves replacing the actual scores of the data with a rank after the data are sorted. One thing that's very important to note is that non-parametric tests do assume that the data distributions for a two-sample test come from the same distribution as each other, so they have the same shape, and I'll show you a picture of this in a minute. This information is in the Whitlock and Schluter reading that has also been assigned. So with the Mann-Whitney U test, again, we're thinking about the logic of this. We would use that instead of a two-sample t-test when the data violate the assumptions of normality. But the general logic that we would follow in order to do the statistical analysis is the same as the parametric t-test that we've already learned. So constructing a statistical hypothesis, establishing a decision rule, calculating the test statistic, and then looking at the probability of obtaining that test statistic, comparing it to our decision rule. But it's important to remember that with these non-parametric tests like the Mann-Whitney U, that the sampling distributions are based on ranks and not quantitative scores. So the procedure is very simple. Our null hypothesis is that the population distributions are the same, and our alternative hypothesis is that the population distributions are not the same. So here's an example of two distributions. The one on the left would be an example where the population distributions are the same, they're identical. So here we have some scores, these are frequency distributions, we have males and females, and they're overlapping perfectly, right? So there's no difference between those population distributions. The image on the right has the same shape, remember that's an assumption of this test, but the location of them, so where the scores are falling, are different. So we can see that in this case, females are tending to have higher scores and the males are tending to have lower scores. So if we ranked all the data, females would tend to have higher ranks than the males. That's what we're looking at with the Mann-Whitney U test. So when we're doing this, we need to rank all the data if they're not ranked already. And to do this, we need to pool the data from both groups. And so, for instance, if you had two groups with 10 scores each, you would rank your data from 1 to 20. If there's ties, you calculate the average rank and then give all of those tied scores the same rank. And so here's a quick example with 6 numbers. So if the data was 4, 5, 6, 6, 6, 7, then the ranks would be, again, from lowest to largest, 1, 2, 4, 4, 4, 6. So because 4 is the average rank for 3, 4, and 5. And then we would sum the ranks for each group. So we'll see where the scores would fall out for each group. And remember, the null hypothesis is true, then the sum of the ranks should be equal when the sample size is the same. So our null hypothesis is that the population distributions are the same. Another way to say that is that the rank of an observation, so a data point, does not depend on the group to which the observation belongs. So if we have males and females, the rank of that observation point, if the null hypothesis is true, should not depend on what group it is. So here, again, are these two distributions. What we're seeing on the right-hand side is that the females will tend to have larger ranks, and the males will tend to have lower ranks. So if we had data that looked like that on the right-hand side, we would likely reject the null hypothesis because the sum of those ranks would differ considerably, right? Because the females here have higher scores, they have higher values. So the sum of all those values will be larger than the sum of the values for the males. Of course, we'd go and look at the tables to see if it's statistically significant or not, and that's important. However, for the logic of the Mann-Whitney U test, keep in mind that we're looking at the population distributions and we're looking at ranks. So it's where those ranks are falling out. That's key.